Hello, everyone. I hope that you're enjoying the VTC 2020 Fall Virtual Conference and that you are staying healthy and safe. My name is Alvin Chin. I am an AI and emerging technology researcher at BMW Technology Corporation, and I will be the moderator for this panel on standards for connected and automated driving. This panel is a continuation of the panel on standards from last year's VTC 2019 Fall Conference in Hawaii. There is much research and development for connected and automated vehicles, CAVs, by vehicle manufacturers, OEMs, and internet companies. However, there is a lack of technology standards on how to develop, test, and validate CAVs, how to ensure interoperability, and how to guarantee safety and reliability. As a result, the IEEE VTS Automated Vehicle Standards Committee, VTS/AVSC, was formed in November 2019 to address this. In this panel, speakers from standards developing organizations, industry, research centers, and academia will provide an overview of some ongoing standardization efforts of CAVs and what the IEEE VTS and AVSC Standard Committee is doing. So today we have 4 panelists. Our first panelist is Ricardo de Castro, who is the chair of the IEEE VTS AVSC Standards Committee and works in the German Aerospace Center. Our second panelist is Alex Wyglinski, who is a professor at Worcester Polytechnic Institute and is the past president of IEEE Vehicle Technology Society. Third is Jack Weast from Intel, who is the chair of the IEEE P2846 Working Group on Assumptions for Models in Safety-Related Automated Vehicle Behavior. And finally, we have Kirsten Matheus from BMW. Each panelist will be giving a talk around 15 minutes, and then we will have a question and answer with each of the panelists. So I will give each of the panelists a question, and the panelists will then answer the question. So please give a warm welcome virtually to our panelists.
All right, so hello everybody, my name is Ricardo Castro. I'm the chair of the IEEE Automated Vehicles Standards Committee, and today I would like to introduce you to our activities. So my presentation is going to be divided in 3 parts. I'm going to start by giving a bit of background information about our activities, outlining the mission of our committee. In the second part, I'm going to talk about 4 standardization activities that we have active right now. 2 related with the testing and validation of radar and LiDAR sensors. Another one about assumptions that are used in the validation of EV models and algorithms. And the last one dedicated to edge computing. And I'm going to conclude my talk with an outlook for future work and also with a call for participation in our activities. So connected and automated vehicles is a very important topic for our society. This is visible, for instance, in the publications. In our transactions, we have a special series dedicated to this topic. We also created a conference a few years ago to have a forum to discuss the latest progress within this domain. We also have an ad hoc committee that intends to develop community with interest in this topic. And also from an education perspective, there are several webinars available in our website produced by the members of our society that introduce and present advances in this domain. And the last dimension that I would like to touch here is standardization, which sometimes is less visible in comparison with conferences and publications, but also very important from a practical perspective. And in our society, there are several standards committees dedicated to rail transportation, also another one dedicated to intelligent transportation systems, and the automated vehicles is the most recent one. So our committee was created in 2019, almost 1 year ago, and it received a mandate from the Vehicle Technology Society as well as from IEEE Standards Association to develop and promote standards in AV technology. And our committee covers several areas, starting with sensing, so algorithms and devices to perceive the environment around the vehicle. Also decision making, how to go from A to B without colliding with obstacles and in a safe way. Testing and validation, so how can you ensure that your algorithm or your device operates as expected. Data protocols, so for exchange of information between different vehicles or between road participants. And also human-machine interaction is another point that we cover in our committee. And so these are the main areas that we are promoting right now. These are the officers in our committee. My name is Ricardo Castro. I am from the German Aerospace Center and I'm currently serving as chair of the committee. The vice chair is Alex Wyglinski. He's the past president of our society and also professor at Worcester Polytechnic Institute. Alvin is from BMW Technology Corporation and is currently serving as secretary. And we also have Tom Kuriara as the VTS Standards Committee Chair and is guiding us in this process of creating standards. And from the IEEE Standards Association, we receive the support from SOGI. In this slide, you can see the overview of the ongoing activities that we have right now. It is divided in two dimensions. In the horizontal dimension, you can see the different maturity stages that we have in the projects, ranging from project proposal all the way to approval and maintenance. And in the vertical dimension, you see the different areas that our committee covers. And so you can see that our projects are scattered along these two dimensions. Some standards, especially the testing of radar and also the edge terminals, they are still at an early stage, still approving the project proposal. The second sensing project about LiDAR technology is already a bit more advanced, and they are now trying to create or mobilizing a working group and attract critical mass to the standard. And the last one, the P2846, which is defining assumptions for models of AVs test cases, is even more advanced, and they are already drafting and preparing the standard. And so in the next minutes, I'd like to briefly talk about each one of these projects that we have going on. So the first one is the P2936, and it's the standard for test methods of automotive LiDAR performance. So LiDARs, they emit light pulses that are reflected by obstacles, and by measuring the time that it takes for the pulse to be detected again by the LiDAR sensor, we can estimate the distance to the object. And so by repeating this process several times, we're able to build this kind of point cloud information. And so in this standard, the goal is to define and propose a test method that can help us measure performance of LiDARs. So for instance, we are interested in measuring precision and resolution of this kind of point cloud. Also testing range, minimum maximum range of the LiDAR, defining probability of detection, among other features. And we hope that this standard will help us compare and benchmark different LiDAR technologies or different LiDAR devices. And our committee is the main sponsor behind this project. The first meeting of this working group is going to take place next month. And they are still looking for a vice chair and a secretary. So if you have interest in these kind of topics, I'd like to encourage you to get in touch with Zhao Xin. He's leading this activity, and we'll be delighted to hear from you. The second project I would like to briefly touch is related with testing of radar. We just approved a project that focused on automotive radar performance metrics and testing for verification of autonomous driving and others. And so radar, they have a similar goal as LiDAR, but they use radio waves instead of light pulses. And so in this project, we want to define test methods, also to measure performance of radar. And one particular topic that is covered here is interference between multiple radars. So especially with the widespread use of radars in vehicles with high degree of automation, they might start to interfere with each other. So in this case, for instance, imagine that you have a radar installed in a vehicle coming in an opposite direction, or a radar installed in the back of a preceding vehicle. And if these radars, they share the same, let's say, channel properties, they might interfere with each other and disturb the detection of range and other signals in this process. And so one important point that we are going to cover in the standard is to measure this interference and also mechanisms to mitigate this interference. And this standard is being sponsored by our committee as well as by the IEEE Instrumentation and Measurement Society. And if you want to know more about this work, please get in touch with Fahime Rafiania. She's the chair of this working group, and she's moving forward with these topics. The third standard is the P2846 with the title Assumptions for Models in Safety-Related Automated Vehicle Behavior. And so here, the goal is to look into use cases that you use to validate AV technology. Often you need to include other road participants, other vehicles, or pedestrians and cyclists. And you also need to assume behavior for these road participants. You need to assume what is the relative position, what is the velocity, what is the acceleration. You need also to assume what are the bounds for these variables. And in the standard, they intend to propose these kind of bounds and specify these bounds that can then be used for the validation of safety in AVs. And this activity is being sponsored by the IEEE Vehicle Technology Intelligent Transportation Systems. They are the main sponsors, and our committee is co-sponsoring this initiative. The chair of this working group is Jack West, and if you have interest in this topic, please get in touch with him. He's also presenting a talk in this final session, where for sure he's going to go into more detail about the activities in this standard. And the last project I would like to briefly touch is related with edge computing. So over the last years, there's been a move bringing cloud computing a bit closer to the vehicles, a bit closer to data sources in order to decrease latency and also decrease bandwidth, which can be very important for cooperative driving scenarios. And then in this project, we intend to develop information interfaces, especially between the edge terminal and the roadside sensors and the vehicles. And we also intend to develop requirements and the reference architectures for use cases that rely on edge computing. So for instance, cooperative motion planning or data fusion are some of the use cases that we have in mind. This activity is being sponsored by the IEEE Consumer Electronics Society, also from our committee. And if you have interest in this area, please get in touch with the link below. What is the outlook for our work? So one goal that we have is to help all these projects that I just presented move through different standardization stages. So at the end of the day, we want all of them to reach standard approval and then maintenance. And some of them might reach this stage a bit faster, especially the 2846 about assumptions for EV models. They might reach approval next year, and the others might take a couple of years to reach the same state. And the second priority for us is to bring more projects and to diversify our portfolio of standards. There are many opportunities in test validation, decision making, sensing, There are several standardization gaps that still need to be addressed when you think about the use, for instance, of machine learning in these areas. There is a huge lack of standardization, and so if you have interest in these topics, please approach us. I will be delighted to support your initiatives. And in fact, this links well with my last slide, which is a call for participation in our activities. And you can get involved in different ways. You can join an ongoing standardization project. So all these 4 projects that I showed here, they are open, so anyone can join, as long as you're an IEEE member. You can come from the industry, from the university. You can participate in some standards at an individual basis, other standards at an entity-based, but it's an open environment, and so it's a great way to get involved. Another one is perhaps you already have an idea that can be standardized, and the barriers to start a standard project are very low. So you only need 1 page proposal where you outline the scope, the need of the standard, and then you need the support and endorsement of 3 people or 3 entities. So it's also a good way to start. And the last option is related with the pre-standardization activities. So perhaps you have an idea for a standard, but you don't know if it has potential to be a full standard, or perhaps you need to mature the idea a bit more. And one instrument that we have available is the creation of study groups to do that. Another point I'd like to highlight is we also cooperate actively with the IEEE Standards Association, and they also have events every year, 2 or 3 roundtables, also workshops, where you can come and discuss with people from standards, from industry, from standardization body organizations, and discuss gaps and discuss potential projects. And so this could also be an interesting opportunity to get engaged in this type of activity. And so thank you very much for your time and attention. This is the end of my talk, and I'm looking forward to questions and comments. Thank you.
Hi, everyone. My name is Alex Wyglinski, and I'm a professor of electrical and computer engineering here at Worcester Polytechnic Institute, or WPI. I'm really honored and excited to be part of this panel on autonomous vehicle standardization activities and talk about the academic perspective of connected and autonomous vehicles. So over the next several minutes, I'll provide a little bit of insight as to how the academic community looks at connected and autonomous vehicle technology, right? So as academics, sure, you know, we tried to do some applied research and development and kind of take fundamental concepts and then convert them over, translate them over to the real world, to actual practical systems that solve really technically challenging problems, right? But our focus, right, like every academic, like every sort of research project, always looks at high risk, high return type of issues, right? So what we're looking at is not the time frame of 1 month, 3 months, or 6 months out, where we need to have a product right now that's deployed in the field on 100,000 vehicles. No, we're looking 5 years out, 10 years out, maybe 20 years out. Perhaps it never gets realized. But that's the nature of what we do. We look at things and then apply something really kooky potentially and say, what would happen if we were to apply this thing, okay, to this challenging issue, right? And over this slide, these slides, this presentation kind of gives a little bit of insight, and in particular, a little bit of my own work as to what I mean by kooky, by like things that like, how does that fit into all of this? I'm going to mention the word bumblebees. Heck, how does bumblebees fit into connected and autonomous vehicles, right? Okay, so let's get started. Okay, so first of all, self-driving cars. It's like self-driving car technology itself has actually been sort of explored, tested out, and road experiments and the like. People have like patented technologies ever since really the beginning that we've had automobiles, period, on the road, right? Like for instance, in the 1920s, there was this thing called phantom car. vehicle that can drive without any human assistance. So there's a lot of potential behind this technology, right? Everything from like reducing the number of fatalities on the road due to human error, the potential of having vehicles support humans and transport humans that either don't have the economic means, do not possess the ability to drive, even the ability to eliminate things like rush hour traffic because of how they optimize their road behavior in terms of like perhaps their platooning, perhaps the way they space themselves out in an environment in order to maximize traffic flow from somewhere in the suburbs down into, let's say, some urban population center or a workplace, and then vice versa on the rush hour out. So self-driving cars has received a lot of attention, especially in the last 5 years, right? And you have a growing number of companies, both traditional automobile manufacturers as well as startups who have no history of doing anything with automotive systems whatsoever, exploring this area, creating new advances, releasing new products, testing them on the road, right? So it's very exciting, and this is one example here. Like Google is one now. Waymo is one of several companies that are deploying these vehicles on the road, right? So to me, there's like a ton of technologies out there, right? So obviously, computing technology, huge, critical, if you will, in terms of the ability for these vehicles to process data, lots of data, and make decisions on the fly, right? So obviously that's tied in very, very closely to the advances that are predicted and follow Moore's law, right? So without the latest advances in computing technology, that's one key ingredient that has fueled into self-driving car technology. But another really, really important technology, I would say, is kind of like the complementary technology to the computing technology is sensor technology, right? The ability to have full or nearly complete situational awareness around each vehicle in order to say, oh, I'm in rush hour traffic. Oh, there's a vehicle to the left of me, ahead of me, behind me. There's a bus on this lane that's quickly passing me on that side. I'm in this lane and I'm heading that way and I'm located over here on this highway. All of these technologies are critical, right? Self-driving cars cannot make decisions on what to do if they're blindfolded, if they have no situational or minimal situational awareness information. So they've got to, this is a critical ingredient, right? So with the situational awareness information, it gets all sampled, it goes into the processing technology, it's fused, right? The algorithms that sort of say, this is what my landscape looks like in terms of a self-driving car in its relation to its environment. And then it translates it into action once it goes into algorithms like motion path planning, nonlinear control algorithms, because vehicles, they don't stop on a dime. It's like vehicle stop. Well, if you're going 75 miles per hour, try and go 75 miles per hour and then suddenly brake. You're not going to like stop right away. You're going to have a lot of mass that keeps on moving that vehicle because of the friction coefficient, the road surface, the type of tires you have, perhaps there's snow or black ice, any one of these factors, right? So the sensing technology takes this information, it translates it into the situational awareness data. There's some sort of decision maker translated into action through a variety of control algorithms. And then what ends up happening is like the vehicle now interacts with the environment around it, right? And it's got to do this continuously forever and ever and ever as long as the vehicle is in operation. Oh, and by the way, if you have other self-driving cars, now it's like a concert. Now it's a big dance hall, if you will, on a roadway with self-driving vehicles, oh boy, as well as still human-operated vehicles. It's not like you're going to throw away cell phones. Vehicles, a lot of folks hold on to their vehicles for what, like 5, 10, 15 years? Well, 15 years is a little bit of a stretch. So you're going to have a melange of both human-operated and self-driving vehicles on the road for years to come. So sensing technology is critical. And so this is what everybody's then praising LiDAR. It's like, hallelujah, LiDAR is fantastic. Wow, LiDAR is awesome. I can see all this stuff. See, this is what my vehicle sees of the environment around it. Plus, in addition to LiDAR, you have vision systems and you have radar and a number of other technologies. And why are we doing all of this? Because of human fatalities that occur on the road due to human error, which is like 36,000 people that die per year in road accidents, and a lot of it, the majority of it, is attributed to human error. So take human out of the driver's seat, almost literally, and you put self-driving cars into the fray, and what ends up happening is potentially you should see a decrease in that. But, if you don't have complete situational awareness, again, it's like you driving a vehicle and you're doing this, or you're doing this. If you don't have complete sensory awareness of what's around you, you can have the best control algorithm, you can have the best data fusion center, you can have the best sort of actuation resulting from all the decisions being made on your vehicle, and it still doesn't matter. You need information. You need information, right? And the problem with the sensing technologies, like on the left, radar, like in the middle, vision systems, and like on the right, LiDAR systems, although LiDAR systems are probably way better than that one, is that they only see as far as the first object that they see, and they can't go beyond that. They're all line of sight technologies, right? So we need some sort of sixth sense. Let's take advantage of today's technology in order to really extend that situational awareness well beyond the first vehicle I see in the front, the back, the sides, the building, the trees that block my field of vision, my sensory awareness, my situational awareness. So folks, that's where wireless connectivity comes in. And this, in the academic community, has been an extremely exciting topic for at least a decade because of the promise it holds, right? So humans don't have this sort of like, sixth sense. Well, some claim to, but in reality, I can't see behind a building, right? Imagine a vehicle can. Imagine a vehicle has complete situational awareness of where every other vehicle is, like along 1 kilometer or 1 mile stretch, forward, backwards, and everything feeding into it. Wow. Like that type of awareness and what every other vehicle is thinking, like that sort of hive mind approach is critical. But lots of issues with connected vehicles, lots of issues, lots of potential, but this is a huge, this is a huge research area. And the idea of doing vehicle-to-vehicle communications, especially around things like buildings and such, is really important. Like buildings, complicated intersections, like whiteout conditions due to snowstorms, nighttime conditions, environments where one or more of our line-of-sight sensing technologies just doesn't cut it, right? Vision sensors at night, already you're at a loss, right? Impaired conditions with our radar systems. If you have crusty ice on your bumper, also a very big problem. Or if you have interference due to millimeter wave communications from nearby, let's say 5G base stations, right? And then LiDAR, again, LiDAR is like, it goes as far as whatever it reflects against, but not beyond that, right? If you go to the LiDAR, like what's behind stuff? Well, that's kind of like unknown. There's a higher probability something is behind there, but you can't see it because you've just, it's behind what the LiDAR can perceive, all right? So, and there's this idea that we'll have some vehicular Internet of Things, right? Like information, this is an example. This is actually WPI campus, a really bad image, if you will. Like this is in Worcester, Massachusetts. Every little colored line, if you will, is a communication link with another vehicle. Imagine you have this internet mesh. And now this is one architecture. People have talked about doing cellular V2X, where you share it over a cellular network, this information, right? And that's possible. Like, and there's already releases out there in 5G that enable it, as well as vehicle to vehicle, especially in things like IEEE 802.11p. Right? And as well as 5G is talking about that vehicle-to-vehicle connectivity. But nevertheless, the ability for vehicles to share information with each other is super critical because of that sixth sense, that situational awareness that will go beyond what humans perceive. This is going to be the game changer, and this is where the academic community is focusing on the hard problems, like channel modeling, like designing ways of, very importantly, coming up with error-free or minimal error communications between the communication links. How do you share that information? My personal interest is in, do we have enough wireless electromagnetic spectrum to support all those vehicles doing crazy maneuvers, not crazy maneuvers, but lane changing, which is very challenging. How do we know I have enough electromagnetic spectrum? I'm already fighting out with all these other wireless applications in order to do something like car 1 trying to go into the right lane, but it needs to inform car 3 that's quickly accelerating into the space, and car 2 and car 4, right? So what ends up happening is, like, do I have wireless spectrum? Because if I don't, I can't communicate. I lose my sixth sense ability, right? This is a very challenging problem. And this model, everything is based on access to wireless spectrum. In the United States, we have 75 megahertz of spectrum at the DSRC band, which already is like being carved up and minimized and stuff. So how do we get wireless access to wireless spectrum for a vehicle-to-vehicle or vehicle-to-infrastructure or vehicle-to-anything communications? This is a hard problem. This is a hard problem that will extend for years. How do we do this and coexist with other wireless applications? How do we do this and achieve low latency communications? Because a message that says you're going to get into a car accident in less than a second, but the latency is 1 second, is no use to me. So this is where we play. And it's situations like this that worry me. If all these cars need wireless connectivity and we have a collision event that we need to inform everybody around us, right? So that is one of many different topics that we look at in the academic community, and the hard topics. Like, we definitely look at theoretical bounds, and we do computer simulation modeling. Heck, we even do like hardware experimentation in the lab and maybe on the road. Like, for instance, this here is like my grad students in 2011, we did a little bit of V to V to V to V multi-hop communications in the 2.4 gigahertz band. I know it's not it's not a vehicle-to-vehicle communication band, but nevertheless, just like, you know, back of the envelope, does multi-hop routing work in a vehicle context, right? So I'm going to look forward to talking a little bit about the questions that are presented in this panel. And thank you again. I'm really excited to be part of this effort and this activity. Thank you all.
Hi, my name is Jack Weast, and today I'm going to talk about metrics, methods, and assumptions. Let's consider for a moment what our future with automated vehicles will look like. The original introduction of the automobile was quite a mess. Roads at that time were owned by horses, by people, by wagons, by bicyclists. And so when this big loud machine came onto the scene, it was quite chaotic. It took a long time for us to figure out sort of the rules of the road and how we could coexist with these machines. So how will it work with automated vehicles then? So let's ask ourselves, what if every automated vehicle on the road had a different definition of what it meant to drive safely? What if every state in the US or every country in Europe had their own definition of driving safely? And what if every time there was an accident, let's say involving even 2 automated vehicles, it took a lawsuit and years of court fights to figure out, you know, who was in fact ultimately the one that was driving safely and who was not. The problem is that unless we can come to an agreement on what it means for an automated vehicle to drive safely, there simply will not be automated vehicles. They may stay isolated in small trial deployments or things like that, but we're not going to enjoy the wide-scale deployment of automated vehicles unless we can answer this essential question. So let's consider the role of safety standards to help us figure this out. We can learn a lot from the avionics industry. In the early 1990s, the introduction of automation systems caused a lot of confusion. There were safety incidents. People didn't know how the systems would work, what their capabilities were, the interaction with them. And so the FAA realized that we needed to get ahead of this. And so they created the Commercial Aviation Safety Team, which for the first time ever didn't look at crashes that happened. They dug into these automation systems to proactively identify and understand what risks could exist and how can we best mitigate those to an acceptable level of risk. The results speak for themselves. In the 20 years following the creation of this team, We enjoyed probably one of the safest periods of air travel in the history of the aviation industry. And so the numbers speak for themselves. But it took the FAA convening industry in a safe place to share information and collaborate and define and assess what is acceptable risk before deployment. We have that same opportunity with automated vehicles if we play our cards right. So let's return to this question. What does driving safely mean? Driving safely is driving at a societally acceptable risk balance and proving that you are doing so. As a human driver, we understand this well because this is what we're doing when we take our driver's test. We're showing that we know how to drive. We know how to drive safely. And so it's an acceptable risk to give us that driver's license, even though we're 16 and probably not all that great of a driver. But obviously automated vehicles are going to be quite a lot better. But how much better? How safe is safe enough? What is the level of acceptable risk that the automated vehicle must achieve? The brightest physicists out there to match with extra kinds of sensors and things in this vehicle, lots of great capabilities. Human drivers learn tricks, things like the 2-second rule. That's where you're following a lead vehicle and you start counting the number of seconds after it passes a certain marker to see when you reach that same marker. And the idea is if it's 2 seconds at least, then you're at a safe following distance. But even humans know that generally this isn't always true. What if you're traveling at a very high rate of speed on an icy road? 2 seconds is definitely not going to be enough. And so with automated vehicles, we can be better. We have the capability to answer more precisely something like, what is a safe following distance? So here's the safe following distance formula from the responsibility sensitive safety model that was released back in 2017. And it's based on physics. So we've got objects of mass in motion, velocity, acceleration, braking, reaction time. We can piece that together into a parameterized equation and calculate much more precisely a safe following distance. So then who should decide how safe is safe enough? What is a following distance that is safe enough? What following distance represents the level of acceptable risk? So if we go back to this formula, we don't need to know all the details, but it's important to note that most things in the formula can be measured or known. The automated vehicle knows its own capabilities. The automated vehicle can measure the position and velocity of other vehicles. But what it can't measure or know is what is the maximum deceleration rate that I should assume is possible for the vehicle that I'm following. And so this is where you need to make an assumption. And so what should you assume? Different vehicles have vastly different braking capabilities. So if you've got a Porsche 911, your car can brake 12.5 meters per second squared. If you've got a Ford F-150, you're down around 8. Older vehicles could be less than that. So what do we assume? Should an automated vehicle assume the global maximum worst case? What if that's 25 meters per second squared because somebody's got a race car on the road? Well, if we did that, it would be extremely safe, right? Because then we could make sure that because we picked that global maximum, we will never crash into the rear of a vehicle that we're following because we're accounting for that global worst case. But the problem is what happens then? Automated vehicle is going to have a very long following distance. It's going to drive everybody crazy on the roads. It's going to contribute negatively to traffic flow. And people will be calling for these automated vehicles to get off the road because they drive so conservatively that nobody wants them around. Alternatively, we could choose a value that's more naturalistic. Interestingly, NHTSA did a study and they found that regardless of what vehicle you're driving, humans brake on average with a low standard deviation of around 6.5 meters per second squared. So should we assume 6.5 meters per second squared, a naturalistic following distance that fits into traffic flow? But doing so means we are accepting a non-zero risk that a crash will happen if a vehicle were to brake at a level much greater than that. And is that okay? How safe is safe enough? And so here's where industry can help by defining these parameters, but ultimately we need government's help to pick the values. And government does this all the time. When a new road is built, a speed limit is picked. That speed limit is a balance between safety and usefulness that represents acceptable risk. If we wanted to eliminate traffic fatalities around the world in human-driven vehicles, we could set the global maximum speed limit anywhere in the world on any road to, say, 10 miles per hour. Be extremely safe, right? Be great for safety, terrible for usefulness, right? So these values represent a balance. New regulations are calling for electric vehicles will be required to emit sounds when operating at a low speed so that pedestrians can hear that the vehicle's coming. They picked 62. Why 62? Why not 65? Why not 70? If it was 80 or 100, would more people hear it? Would we increase safety? Probably. At the expense of everyone's hearing. But why 62 and not 50, not 40, not 30, right? At some point you have to pick a number that represents acceptable risk. And this is what the FAA did. And here's how we have the opportunity to do that here. Which is why I'm very proud to be leading IEEE 2846, a standard that is documenting these assumptions that are essential for safety models that are used in AV behavior. We have an incredible collection of companies that are participating, and I'm honored to be chairing this committee with my vice chair from Waymo and my secretary from Uber. Maximum acceleration. Pedestrian also maximum. Maybe they're where the position might be. We all had situations where we're driving, say, 45 miles per hour on a road right next to the sidewalk with a pedestrian on it. How do we know that they're not going to change the road? Heading angle rate change. We intuitively know that if they're on the sidewalk, they're going to stay on the sidewalk if they stay within a certain limited deviation of their heading angle rate change. So this illustrates the values of these assumptions and why we need to make them, not just as human drivers, but why machines will need to make these as well. So in summary, we call on industry and government to work together and align on what it means to drive safely. We need to continue driving forward these consensus-based standards, and the research community can play an important role in helping us identify what are methods for which to derive these values that plug into these parameters that are used in safety models that are driving on the roads, hopefully very soon near all of us. So thank you for your time. I look forward to the discussion.
Ladies and gentlemen, my name is Kirsten Matheus, and I have the honor to talk to you about the status of automotive Ethernet in 2020. So the car industry right now is facing a time of major challenges. On one hand, the car industry has ever fiercer competition to deal with. And on the other hand, there's a digitized world with all its possibilities that the industry needs to embrace. And with the digitization, I mean that the new currency is data and software, and that this can change everything on how we see mobility, and that it also changes the way we offer cars, the products and the services, but also the way we build cars. And we develop cars. So there's huge changes involved in this. And that also leads to new requirements in the EE infrastructure inside the car. And the EE infrastructure is also strongly entwined with the in-vehicle network. And in all these challenges, Automotive Ethernet provides the right infrastructure to support meeting both goals, being competitive and being able to embrace the digitization and what it offers. And there are some very obvious features like over-the-air update, which sells customers the most recent functions. And of course, over the air is not necessarily Ethernet over the air, but it's the whole system that allows for this. You have software virtualization, which allows for the most efficient use of available hardware. And you have service orientation, which allows faster development of new functions. And the whole network is flexible, self-learning, and gateway free. So those are some of the really key features that Automotive Ethernet allows. The automotive industry, first of all, introduced Automotive Ethernet for its physical layer speed. And you have quite a number of car manufacturers by now who have gone public with having Automotive Ethernet in series production cars. And you have a list here that's, I don't think it's a complete list. I think there are more, which simply I don't know about or that haven't gone public. And you have a large number of physical layer speeds too that have been developed and that are still being developed. It all started with the broad reach, the 100 megabit Ethernet that was completed in 2011/2015, depending on whether you take the Open Alliance or the IEEE version. And it had its first SOP in 2013 at BMW. And right now, I think there are at least 18 OEMs that have introduced Automotive Ethernet, this technology. Then you have 1000 base T1 that was completed in 2016. I think the first SOP was 2019, and you maybe have 2 car manufacturers now. You have the optical version of the gigabit completed in 2017, and now I think in 2019 it saw the first introduction. And you have the 10 base T1, 10 megabit Ethernet completed in 2019. Might be introduced in 2024, 2025. And of course, as that is in the future, there are no car manufacturers available yet. And likewise for the 2.5, 5, and 10 gigabit, which was completed as a standard in 2020, and where you might see introduction in the same time frame, 2024, 5, 6. And then you have 2 more projects. You have one for electrical larger than 10 gigabit per second Ethernet, where the task force has started, and you have for larger than 1 gigabit optical, where also the task force has started. And of course, you have no SOP available in this. So, does that mean it's all good? It looks promising, it certainly does. However, there are a number of challenges. One, of course, is you've already seen on the previous slides, that is that the speed grades need to be completed a long time before they're actually adopted. So you have car manufacturers right now who have the first adoption in the car and are facing 4 new standards that they might introduce. But the other point is really that the 100 megabit technology had a sweet spot. If you here look at a chart with a number of other in-vehicle networking technologies or technologies that are sold for communication in the car, you can see that the 100 megabit is a bit isolated here in its use in the middle, and it did meet a sweet spot. If you go to this other area, the higher data rates, you have a lot of other technologies, and likewise in the lower range. Of course, in the higher data rates, many technologies are point-to-point, and I'd like to point out that you have the SerDes technologies here, where you have an interesting new activity, the Automotive Alliance, where you find a slide in the backup if you're interested. But here for the 10 megabit, for example, you have a number of competing technologies that can handle very similar use cases. That's challenge number 1. Challenge number 2 is that originally Ethernet did not support quality of service. Of course, since 2004, the IEEE 802.1 has developed a number of specifications that support a multitude of quality of service options. And this is new in the industry. In legacy technologies, you generally have one quality of service for one technology. If you look at FlexRay or most, they always have, they're designed for cyclic data, and that's what they support best, and everything else is a bit difficult if you want to do it. If you have, but that actually might not be always the latency or quality of service requirement you need. You might actually be that you just need a latency that's before a maximum value, or that you always need the shortest latest possible, or that you even only just need to know when data was generated and you don't really need to know. It doesn't actually need to be cyclic. Then there is a number of communication paradigms that are new with Ethernet and that the industry hasn't really got used to. One of the topics is broadcast. Legacy technologies like CAN or FlexRay use broadcast only. And of course, broadcast is a simple approach in data transmission because you doesn't need to know who actually is the recipient. And that saves address space in the overhead, so your overhead is smaller. And of course, if all units always need to receive all data, that's also efficient if you then send a broadcast message to everybody. However, the broadcasting unit doesn't know who actually consumes the message. That can be a privacy concern, or they might not even notice that an intended recipient is not part of the network. How do you do that in a broadcast network if you don't know who the recipient is, whether that recipient actually received the message? And of course, it wastes bandwidth in very large networks where only some units might be interested in the data. And if your network is limited size, as the industry started with, that's all good. But however, if you have large modern networks, you just need to add a lot of overhead outside the technology to do exactly what this technology just doesn't do. For example, add recipient. If you go across a gateway, or if you have a large network, or you want to do software updates, you suddenly need to know where exactly is the recipient of that data. Otherwise, how do you know the software is correct? Or you need to do it on higher protocol levels. Everything that Ethernet does on the basic level. And of course, security needs to be added outside the transmission technology as well. Ethernet, in contrast, allows for unicast, multicast, and broadcast, and it's a self-learning network, so you don't even have to do all the gateway bookkeeping outside of the network itself. Another very important part is the service-based architecture, and service-based means it's a separation of concern. If you want to do, for example, a brake assist, if you have a signal-based system, the brake assist needs to know which sensor is available where and with what quality, and needs to ensure that the whole chain from the sensor to the brake assist works well. If you have a service, the brake assist doesn't know which sensor actually generated the data. It needs the service, the scenario ahead of the car in 50 or 100 meters, or whatever velocity you want to support for it. So it doesn't need to know, and that makes it easier. It also makes it easier to add on new functions or features in later times if you are interested in that, and that makes it very efficient and very good. You have another challenge also, and that's the architectural changes. So there is a trend towards centralization in the car industry, and if you do that, it affects the network in various different ways. I don't want to go into the details, but it needs to be observed, and people need to look at it in detail. Also in interrelation with the networking technology. So, the car industry introduced Ethernet in order to support the demand for higher data rates. And the most important hurdle on the physical layer is being successfully handled. So that's very good. However, the true advantages of Ethernet are not in the physical layer, but it changes the modern EE architecture. It allows for service bases, it replaces gateways, it has state-of-the-art security, and it has a strict hardware-software separation, which allows for scalability and flexibility and reuse of protocols independent of speed. And here the automotive industry is still at its beginning. So with that, I'd like to thank you for your attention. And just 2 quick notes. There is a book available in which some of these aspects are being described in English and Chinese in China. And this is the information about the Automotive Service Alliance if you're interested. Thank you once more.
So thank you to our 4 panelists for giving the talks. Now we're going to have the question and answering period. I will give 3 questions to each of the panelists, and they will then answer each of those questions. So the first question to each of the panelists is, what do you see are the major challenges to developing standards for connected and automated vehicles? Is the challenge technical, legal, government, institutional, economic, or social?
In terms of challenges for adoption of AV technology and AVs, I believe that technical challenges are still ahead of us. No one really knows how to design a safe AV at an affordable price. So I think there are huge challenges in terms of perception, decision making that remain open from a research perspective, also from an application perspective. And so I anticipate that it will take a while until all these corner cases that exist in AV technology are really eliminated. Also legal challenges, I think they are quite interesting. If an AV has an accident, who is responsible? Is it the engineer? Is it the company that produced the AV? Is it the end user or the buyer of the AV? So it's not yet very clear to me where the responsibility is going to lie. Also, I think from a social perspective, it's also interesting to see if AVs are going to be accepted on the long run. So it's interesting in the sense that vehicle automation sometimes is not well accepted in some areas of the world. So for instance, when you think about manual gearbox versus automatic gearbox, people in Europe, they still like to have manual control over the gearbox, while in America and other parts of the world, automatic gearbox dominates. So I could also see that in the future, there might be some areas in the world where, let's say, people, they prefer to drive fully manual instead of AVs. So I think for acceptance of AV technology, there might be some cultural and geographic aspects playing a role.
All right, so for me, the major challenges with respect to autonomous vehicle standardization efforts, the big one is different regulations and different laws from state to state to state to state, right? Let's, like, for instance, look at autonomous vehicle testing. Wildly different from different states. Like, for instance, Massachusetts, very structured, very organized. Like, if you want to do anything with autonomous vehicle, you have to go through a set process in order to deploy your autonomous vehicle, and it's very closely monitored by the state, right? On the other hand, there are several other states where it's kind of like the Wild West. It's like, oh, you have an autonomous vehicle? Yeah, okay, you can go out and test it, right? So as an example, I think is kind of important, because imagine trying to now standardize processes, standardize equipment, standardize the way self-driving cars operate on the road. But wait, hold the phone. Different states have different sort of requirements on how self-driving cars operate. So this is going to be a major problem, because potentially you could have up to 50 different sort of personas that a self-driving car needs to acquire as it crosses state boundaries, right? So that's going to be really important. Another issue I believe that is equally as important is also, how do you test self-driving cars, and especially the components you put into them with the corner cases? Because again, I like to think of the self-driving car and the decision-making process that they employ as relatively brittle compared to a human being trying to take past experiences in order to process them to make a decision on how to drive a vehicle in a very extreme situation right then, right there. Right then, right now. And so that to me, I think, are the kind of two critical challenges that are faced by autonomous vehicles, and how to standardize them.
I think the major challenges to developing standards is sometimes technical, but as I presented in my presentation, these are really important societal questions. We as industry can provide the technical tools, the safety models, the standards by which the vehicles can be built. But at some point, sometimes we have to understand what is acceptable and what is not. And that ultimately is a societal question for which we need government's help to solve.
Okay, question 1. To make a standard successful, it needs to have enough market potential. And to have enough market potential, it needs to have a value to whoever uses the standard. And enough market potential also means it has more than one player who can compete in that market. So that might be a huge market, but if only one company occupies that market, it doesn't make sense. So that works well. In vehicle networking, making an in-vehicle network standard successful is not that obvious, because there's a slight conflict of interest between the tier 1 suppliers, who does the electronics, and the car manufacturer, because the car manufacturer is responsible for the in-vehicle network, for its functioning between different units of different tier 1s, and the tier 1 is supplier for supplying the technology that drives the line. So what is easiest for the tier 1 is not necessarily easiest for the car manufacturer, and the other way around. So a tier 1 might actually not be interested in making anything new, in investing in in-vehicle networking technology. Well, for the car manufacturer, it might actually be really important to do so. So that's a difficulty. And yeah, so if anybody knows how to overcome that, I'm interested to hear.
The second question is that the development of standards takes a certain period of time, a long time for creating the standard, for revising it, and voting for the publication of it. Similarly, journal publications can take up to a year before publication, so we are beginning to see open source access journals that significantly reduce the amount of time before publication. Do you believe that standards for connected and automated vehicles can take an open access approach? And would it work?
Open access standards, I'm a big believer in them. In fact, this movement started in software with open source software. It's now spreading to open access publications, and it's a matter of time until it makes inroads into open access standards. In fact, IEEE-SA already accepts open access standards as long as the participants are willing to pay a fee. And so it's, I think it's a great idea. It's something, at the end of the day, standards, it's, let's say, something that will benefit the society. It's something that we are doing for a greater good. And so I believe open access is the way to go, let's say, to disseminate the best practices for constructing systems, especially the ones that are safety critical.
So I'm not sure if we can use the example or draw parallels between open access publishing and standardization. Because I don't think that the length of the review process correlates like it's exclusively an open access idea. I've published in open access journals and the like, where the review cycle was 1 to 2 years long, right? I think that the idea of having a quick review cycle in open access is sort of like an additional benefit of going down the open access route. And it makes sense, especially since how technology quickly evolves rather rapidly. That's why people like publishing in conferences, because they get the ideas out there quickly, while a journal paper, the traditional journal paper, takes forever. And by then, unless the work is archival or seminal in nature, you know, the technology is already kind of like outdated. I would believe that in terms of short turnaround times and being able to create a process where we don't wait too long, we can relatively quickly develop standards, especially in things like autonomous vehicles, such that we can roll out while the technology is still emerging. I think it's vitally important. I don't think we can have sort of that really long time period to vet everything, to make sure that everybody's happy, and then a couple of years later we roll out a standard that, oh, wait a minute, it's already outdated. There's a new technology and has replaced this. So I think learning from the open access publication world, I believe that the standardization process, we should have sort of an accelerated path in order to be timely, the results of our standardization efforts to correlate with the technology as it's emerging in order to make the most impact.
I don't think standards need to take an open source approach. Standards are already open. Most standards organizations allow you to participate freely. I think what's needed is standards to work quicker. I think part of the problem is standards tend to boil the ocean. Take our work group for 2846. We started out thinking about trying to design one safety model that could rule them all, if you will. And we decided instead, let's take a smaller first step. Let's focus just on the assumptions that are common to all safety models. And with that, we bit off a more manageable chunk of work and something that in just about a year, despite COVID and all the other challenges that's presented, we expect to introduce the first edition of our standard. So I think be smarter about how we're doing standards, smaller chunks of work, and focusing on problems that we can agree to solve.
So question 2, it needs to be important that the standard is open, whether that document is published, whether it's a document published at a standard setting organization, at a special interest group, or just published. In the end, doesn't make that much difference as long as enough people can compete. And that again requires that there is a clear possibility or clear knowledge about what happens to IP, how's it handled, how's licensing done. All these items, they're generally set and agreed on in a standard setting organization, but they're often not so clear if it's just a published document. So that makes it tricky. That also sometimes makes open source software tricky. So it needs to be observed, but whichever way works, that's fine. The specification needs to be open, and it needs to be a market of interest, and it needs to be a good document.
And the final question to each of the panelists: how can we ensure the interoperability of CAV standards with each other and ensure that they can cooperate with each other rather than compete with each other?
To avoid overlap between different standards, I think communication is the key. So when you are developing a standard, it's very important for you to do homework, to see what is out there. Also important to reach out to other people, to other standards for the organization, to understand what they are doing, especially to avoid competition and avoid overlap between different standards. So as long as you disseminate, as long as you communicate your intentions with other stakeholders, such that everyone is aware of what you are doing in terms of standards, the overlap potential is decreased a lot. So for me, communication is very important to mitigate these overlap issues in development of standards.
So interoperability is a great question. And I think there's going to be several really key stakeholders involved with respect to facilitating that. At the end of the day, all self-driving cars are going to sort of harmonize and be able to speak with each other, as well as use equipment on each vehicle that interoperate with each other, like are able to connect with each other. And that's going to be the federal government. I think the federal government, like in the United States in particular, like Department of Transportation, but other countries as well, are going to dictate sort of the general framework of what vehicles have to do, right? So I think that is going to be significant motivation in terms of at least bringing, putting sort of a bounding box, if you will, to the capabilities of the different standards, how they should be operating. And then from there, you can start creating points of contact between different standards in order to achieve that interoperability, right? I think others will be obviously the automotive manufacturers. I think they're gonna, because at some point what happens is you can't have one set of cars not be able to connect or communicate or do anything autonomous with another set of cars. Everybody's got to converge, right? And again, the catalyst to this will be the federal government, in my opinion.
Interoperability standards is incredibly important. When we kicked off IEEE 2846, one of the first things we did is identified the need to establish a task force whose responsibility was nothing but ensuring alignment with other standards. And so I think it can be done. I think the industry has changed a lot in the last year or two. Standards organizations are collaborating together. We have a formal liaison relationship in our standard with ISO. And we have other standards organizations that have reached out to request liaison relationships as well with the work that we're doing in IEEE. And so I think everyone realizes that there's no one standards organization that's going to have everything, and that it's going to take multiple standards from multiple organizations. And I think if the chairs of those committees, as I am doing in 2846, are committed to collaboration and complementary standards rather than competing and overlapping standards, it can be done, because the will and the desire is definitely there.
So question 3, interoperability is decisive for the success of the standard. That's, if you do in-vehicle networking, interoperability is the key. That's what you want. So if you don't have interoperability, your standard is useless. And of course, interoperability requires interoperability specifications, and the better the specifications are, the more likely you get interoperability. And better specifications are generally written if there are many people looking at it while implementing, while trying to figure out what it means, so that you get all the disconnects where somebody, the author simply knew what they meant, but everybody else just doesn't, or it can be interpreted in various different ways. So that's where experience in standard writing is good. That's where it's good to have special interoperability specifications too. So the more people look at it, the better. There might be a drawback if you have a published document that's been written by one person. However, that might be faster too, but key is having the same understanding among a number of people and having a good document for it.
So I'd like to thank all our 4 panelists today for giving talks regarding about connected and automated vehicles in terms of for the standards, and also for answering the 3 questions that I had for them today. Unfortunately, we don't have time for further other questions, but if you do have further questions, you can type them in the question panel that you should see in the browser for the session. And then we can take those questions offline and send them to our panelists for them to answer. So thank you very much for watching this panel's discussion, and hope that you enjoy the rest of the conference. Thank you.